Welcome. This is Coach Dorf. Let's continue our discussion about integrals. Last time we mentioned there are two main ideas of calculus. The first idea is derivatives. And we've spent a good amount of the semester talking about derivatives. We talked about the definition of derivatives. We found some shortcut ways to use derivatives. We found some properties of derivatives, and we applied it to some examples. That's the first main idea of calculus. The second is integrals. And we were just starting to talk about integrals, and we're going to continue to do that today. Now, the interesting part here is that derivatives and integrals were developed as mathematical ideas separately, but they turn out to be inverse operations of each other. So they undo each other, just like addition and subtraction undo each other, or multiplication and division undo each other. We'll learn with the fundamental theorem of calculus in a few days that derivatives and integrals undo each other. What are the ideas for what is the main idea of integrals? Well, it's the area under a curve above the x-axis. I want to find the area under that curve above the x-axis. It's going to be in this kind of area here. So it's below that blue graph there, and it's going from A to B, and it's above the x-axis. So this whole area here can be represented by an integral. So that area is equal to this integral, which is written as the integral from A to B of f of x dx. When you see this integral symbol, you can think of it as area below the curve and above the x-axis. Now, we also talked about last time that if your curve dips below the axis, then you can think of it as this part here, A1, and that's going to be a positive area. When it goes over here below the x-axis, that's A2, that's going to be a negative area. This would be A3, and that would also be positive. Let's look at an example of this. Here we have this red curve. We're given four different integrals here, and we're supposed to list these quantities in order smallest to largest. All right, so let's look at this first one here. We have the integral from 0 to 2 of f of x dx. What is that integral? That area is this blue area I'm shading in right there. Now, that's below the x-axis, so it's going to be negative. So that area represents the integral from 0 to 2 of f of x dx, and it's negative. It's less than 0. So if we find another integral that's above the x-axis, we know that this one, this blue one that I just circled, it's negative, so it's going to be less than anything that has a positive area. All right, let's look at this next one, number 2. The integral from 0 to 7 of f of x dx. 0 to 7 means I'm going from here, this part, to there. Now, if I look at this, there's really two components here. There's the blue component that we already talked about being negative, and there's also this. So I can think of this as like area 1 and area 2. Notice that area 2 is much larger than area 1. Also, area 1 we saw earlier is negative and area 2 is positive. So the fact that area 2 is much in total area than the area in area 1, we can tell that this integral here in number 2, the integral 0 to 7 of f of x dx, is going to be positive. And so we know from all that this is going to give us that number 1 is smaller than number 2. All right, let's look at number 3. The integral from 0 to 8. So it's got the blue area, the green area, and then it's got this small like orange in there. Well, that orange area is below the x-axis, and so this is negative. So that tells me that number 3 is going to be less than number 2, because number 3 is the same as number 2, plus I have that little negative area there in the orange or yellow color. So it's got to be a little bit less than the integral from 0 to 7, because we have the same values from the integral from 0 to 7, and then we're subtracting a little bit of that gold area. Does it look like that this third integral, the one circled in gold color, is that going to be larger than the area circled in blue? And I would say yes, because for the gold one, the three components there, if I take the blue component and the gold component, they're negative, but their negative area, I think, is still less than the green one. So I would say that the gold area, the gold integral is going to be circled in gold, is going to be greater than the integral circled in blue. So right now we have then that one smallest, then three, then two. All right, the last one, 8 to 7. All right, what is 8 to 7? Well, 8 to 7 is my gold one. I don't know, I can make it into a different color, but it's the same as this gold one here. So that's all negative. And how does it compare to the other ones? It's since we've talked about that the integral in number 3 is a positive area and the purple one is a negative area, it's going to be less than the one in number 3. But that total area in the purple one is not as much negative area as the blue one. All right, so what do I have? I have 1 is the smallest because it's negative and it's the most negative area. It's the one represented by the blue. Then I have 4. It is also negative. It's one purple and gold there just by itself. It's negative, but it's not as much negative area as the blue. Then I'm going to have 3 because that's a positive total area, but it's not as large as number 2. So that's my answer. Okay, so we have these integrals and it represents the area under the curve. How can we find this area? We can find it by creating rectangles. I'm going to just break it up into segments, and then each of these segments I'm going to make into a rectangle. And so I have like this one, like a green rectangle here, and then I've got an orange rectangle, and then I've got a dark green rectangle and a purple rectangle, and so forth. And you can see that. So what's the area of the rectangle? Well, it's going to be height times base, right? I have a rectangle here. This is its height. This is its base. So the area is just height times base. What gives us the height and base? And that height is the function value, in this case, f of a. The function value, the f of the x value, gives me the height of the function. So the height is going to be f of x, depending what my different x values are. And what's the base? Well, we're going to call the base delta x here. So with the purple triangle, that's delta x. All these will be delta x. And then the area under the curve is sum of all the rectangles. Now, that's just going to be an approximation here. So how can we make the approximation better? Well, we saw last time, if I make the delta x smaller and smaller, so I have more and more rectangles in there, then I get a better approximation. If, for example, I have my curve that looks like this, and if I do 2 rectangles, I get something that looks like that. But now if I do the same thing and I increase the number of rectangles, you can see that my approximation is better and better. Approximation on the right is better than the approximation on the left. What did we do with derivatives when we wanted to get something to be, we make this something small and smaller? We used the idea of limits. And that's what happens here. Okay, how can we make this idea more precise? Well, we'll do the following. We have this definite integral. The definite means that I've got definite numbers, specific numbers there on that squiggly S, the B. That means it's definite, okay, of x. So what we have here on the left is our symbol for integral. And this is now going to be our definition for the integral. So let's look at this. What does this mean on the right? Okay, so first of all, we have this f of x sub I delta x. What is that? Well, from before, we had these rectangles. The delta x was the base, and the height was the value of the x at the function. All right, just like we have here on the right, that red area there, that's the area of a rectangle. It's base times height. The sum, I equals 1 to n of that. We know that this is the area of a rectangle, and then we have the sum of them. So that means what we're doing here is we are adding the areas of n rectangles. How do I know it's n? Well, that's what this is there. So I have the area of a rectangle, I'm adding them and n of them together. And then the last thing we have here is we have the limit as n goes to infinity of this sum, I equals 1 to n of f of x sub I delta x. What does that represent? Well, this limit thing is telling us that we are making the rectangles smaller, which is implying then that we're making more rectangles. And in fact, we're making it approaches an infinite number of rectangles. And so that's what our integral is. So you think about this as here, I've got my curve, y equals f of x, and I'm going from x equals a to x equals b, and I want to find this area under here between a and b and above the x-axis. And now I'm putting an infinite number of rectangles in there. And as I do that, and I'm figuring out the area of each of those, as I do that, I get the value of the integral. That's what the integral is. Let's look at some examples here. When we did this integral from a to b of f of x dx, and we said it was equal to the limit as n goes to infinity of the sum I equals 1 to n of f of x sub I delta x, there are some things here. N equals the number of rectangles, and delta x is b minus a over n, which is the base of each rectangle. So we're assuming that each of these bases are the same. So length or base of each rectangle. X sub I is going to equal a plus I delta x, and we're going to get f of x sub I equals the height of each rectangle. So we're going to use this information now to rewrite what we have here, this integral. This is known as the limit of Riemann sums. This is what we want to get. So we have here on the left, there's our integral, and we want to write it is in there. Okay, so how can I do that? Well, I look at this. What am I given? I first have that my A is 1. So in this problem, I have A is 1. That's in purple. In gold, I'll do B. B is equal to 3. B equals 3. And then I know that, I'll use dark here, that delta x equals B minus A over N. So delta x in this problem is going to be B minus A over N, which is 3 minus 1 over N, which is 2 over N, okay? And that's going to plug in over here. Next, I want to figure out what x sub I is, all right? So where's x sub I? So here's x sub I. It equals a plus I delta x. All right, so what is a? We said a was equal to 1, right? There's a plus I delta x. Delta x is 2 over n. So we get 2 over n. So this is going to equal 1 plus 2i over n. All right, so that equals x sub I. Let's write that there. So we have our x, we have delta x. Again, here's our delta x. And now we have our x sub I. And we just have to figure out what f is. All right, well, f is, there's f. So I look at my original problem, that's tangent x. So f of x equals tan x. So putting these all together, my original problem was the integral from 1 to 3 tan x dx. That's going to equal this limit as n goes to infinity of the sum I equals 1 to n of f of x sub I delta x. And so we just substitute what we have. So this won't change, the limit and the sum. Now, what was f of x? We said f of x here is tan x. So that means f of x sub I, I'm going to use this for x sub I. So it's going to be tangent of 1 plus 2i over n. So we go back here and we have tangent of 1 plus 2i over n, putting that in there. And then the last thing is we have our delta x here. And earlier we figured out that delta x is 2 over n. So we put that in here, 2 over n, and we get this. And so that is our answer, that the integral from 1 to 3 of tan x dx equals that part right there of the limit as n goes of the summation I equals 1 to n of tangent of 1 plus 2i over n all times 2 over n. All right, let's look at a different one. Let's look at it in a different order. So again, in doing this one, I'm going to write down my definition. I've got the limit from a to b of f of x dx. That's my definite integral, and that equals the limit as n goes to infinity of the sum I equals 1 to n of f of x of I delta x. All right, so in this case, we're trying to find the integral, so we need a, b, and f of x. All right, and let me also put in here, sorry, this would be helpful, that delta x equals b minus a over n, x of I equals a plus I delta x, and we have f of x of I. All right, and okay, so what do we've got this and that, all right? And so I'm going to look at my original limit, the one here in blue, that I'm circling in blue, what represents delta x? Well, okay, I'm going to cross things out because, okay, the green things are the same. These purple things are the same. So I'm really left with just two things there in the original limit of the Riemann sums. I'm left with the 3 over n, and then the big parentheses with the 1 plus the square root of 2 plus 3i over n. So one of those is going to be delta x, and one's going to be f of x of I. Well, it's going to be the 3, and let me do it in red. The 3 over n is going to equal the delta x. How do I know that? Well, one thing is I know that delta x will have an n in the denominator, all right, because that's what we have here in the formula to the right. The second thing is that f of x of I has an I in it, okay? And there is an I over here, so that connects to me that this part on the right that I just circled here, that's going to be part of the x of I. So we're going to say then that this is going to give us that delta x, which equals b minus a over n, is going to equal 3 over n. And so that gives me that b minus a equals 3. Now, I don't know what b is, and I don't know what a is yet, but I just know that their difference is 3. So now let's figure out what the x of I is, okay? Well, the xi is going to look like form x of I, going to look like a plus I delta x. And so I'm going to look at my original part here, and I'm going to see what has an I in it. All right, so I'm going to do this in green. This part has an I with it. And that looks like what I'm going to need for the x of I. Maybe it helps think of this too, as again, x of I is a plus I delta x, but delta x is, we found out from before, 3 plus 3 over n. So I'm going to get an a plus 3i over n. Well, going back, it's a little bit hard to see right now, but this green part here, this was 2 plus 3i over n inside that, underneath that square root. So that and this go together, and that suggests that a is going to be 2. And by the fact that a is 2, and I know that b minus a is 3, so b minus a equals 3 and a equals 2. That gives me that b equals 5. All right, so I now have that 3 over n equals delta x. And then I had this 1 plus square root of 2 plus 3i over n. But we know that this 2 plus 3i over n is my x of I. So that's going to tell me that my function f of x is going to equal 1 plus the square root of x, all right, coming from here. And so what I have in the end is a equals 2 from what we got above, b equals 5 from up here, and f of x equals 1 plus square root of x. So using all that, I get the integral from 2 to 5 of 1 plus square root of x. Yeah. All right, so that is my answer on one right here. If you need more practice on this one, go back to the videos from the previous day from section 5.1 and 5.2a, because they talk a little bit more about this. Now that we've talked about that integrals can be represented as the area under a curve above the x-axis, and that we can approximate those with rectangles, and then if we do the limit so that we have an infinite number of rectangles under there, that becomes our definition of the integral. Just like when we did derivatives, after we did the definitions, we wanted to find some quicker ways to solve problems, to solve derivatives. Same thing here. Our definition for the integral is what we just talked about, that it is this limit of these Riemann sums. It's the limit of the area of these rectangles as we increase the number of the limit, and the limit go off to infinity. All right, what are some properties of integrals? Well, first of all, the integral from a to a of f of x dx is going to equal 0. Maybe that makes here. If I have my curve, here's my f of x, and I'm going to evaluate it. Here's x equals a. So I want to find the area under that curve where the base of the rectangle is from a to a. In other words, the rectangle, we've got this little rectangle here. The length of that base is 0. No matter what the height is, if the base is 0, then the area is going underneath the area of that rectangle is going to be 0. So if I have an integral from a to a of f of x dx, it's going to equal 0. Okay, second property, if I go from a to b on my integral, if I want to switch it, and I want to do instead, I want to go from b to a, so I'm changing that direction there, I'm going to get a negative value. Third property, if I've got an integral of x dx and an integral of g of x dx, I can write that as just one integral by adding the functions together. And then the fourth property is if I've got an integral from a to c of f of x dx, and then an integral from c to b of f of x dx, that's going to equal the integral. Well, let's see if this makes sense. Let's look at this picture here. So here's my integral f of x, and I'm going x equals a, and then I have an x equals c and an x equals b here. This area here equals that integral there. This area here under the curve equals this. What can I say then about the integral from a of f of x dx? Well, it's going to be the same. It's just the sum of those two. So the sum of the green and the orange, it's the same thing as just the integral from a to b of the whole thing. So that's our fourth property there. Okay, let's look at this example here. Evaluate the integral from -1 to 2 of x dx. Let's first sketch the graph of this. Here's x, here's y-axis, put in some points, x equals 1, x equals 2, x equals 3, y equals 1, y equals 2. I should put in some x equals -1, y equals -1. Okay, what is my function here? My function x, that's what this is. What's the graph of that look like? Well, that's a straight diagonal line. It goes through 0, 0, 1, 0, and it kind of just goes up like this. Okay. And the integral from -1 to 2 of x dx equals area under curve. So what is that area? Well, it's this blue area and this blue area. But remember that if the area is above the x-axis, like this one, A1, it's positive, and if it's below the x-axis, it's negative. Now, this is easier than just a random integral because what's my shape there? Well, A1 is a triangle, and it's the area of a triangle. And what is that area? Which is 1/2 base times height. And in this particular case, the base B1 here is 2. So B1 equals 2. And the height here, H1, is also 2. So I'm going to get 1/2 2 times 2, which is going to be 4. So 1/2 of 4, which is 2. So that A1 area is 2. What about A2? So it's an area of a triangle, and it's going to equal 1/2 base 2 times height 2. What is the base? B1 is 1. And what is that height? That height is -1. So we're going to get in a 1 and a -1. And so we're going to get 1/2 -1, which is -1/2. And that helps you maybe see why, if the curve goes below the x-axis, why the area is negative. Okay, because my height there is a number. So what is the integral then from -1 to 2 of x dx? Well, it's going to equal a1 plus a2, which is going to be 2 minus 1/2, which is 3/2. Let's look at this example here. So here I've got my function, f of x is the square root of 4 minus x squared. I can think of that as y equals this. What is the graph of that? What does that shape look like? Well, let's square both sides. So if I square both sides, I get y squared equals 4 minus x squared. If I bring the x squared to the other side, I'm going to get x squared plus y squared equals 4. What is that shape? That is a circle centered at the origin of radius 2, right? Because it's the same thing as x squared plus y squared equals 2 squared. So it looks like this, a circle here, centered at the origin, radius 2, both directions, okay? And then what do these limits here, -2 and 2 mean? Well, it means that I am doing the area from here, -2 to 2. So we're doing this, and we're trying to find this area right here. Now, why, you might say, well, why do I pick the upper hemisphere, the part above the x-axis and not the part below the x-axis? Well, that's because the y values here, I can get them, my pen to work there, that y value there, that it's a positive value. Y equals the square root of 4 minus x squared. Okay, if it was below the x-axis, I would do something like negative square root of 4 minus x squared. That would be below, but because it's positive, this means it's above the x-axis. So how can I figure out what this integral is? Well, the integral, okay, from -2 to 2 of the square root of 4 minus x squared dx is going to equal the area of semicircle above x-axis. And it's a semicircle of radius 2. So area of circle, and I'm going to do half of that because it's a semicircle. And that's a circle of radius 2. So that's pi r squared times a half. And r equals 2 in this case, because it's a circle of radius 2. So I'm going to get 4 times a half, or 2 pi for the area there. Let me do one more problem. Let's do this one. So we've got this situation here. Let's look at a diagram of this. So we're going to do there's 1, 2, 3, 4, 5, 6, 7, 8. I've got my function. It's some function. I don't know what it is. We'll just draw in a random one there. And we've got, there's an integral. What does this red area represent? Well, that represents the integral from 1 to 4 of f of x dx. That's what we want to figure out. We also know, we've also got this integral, 4 to 8. And that represents the integral from 4 to 8 of f of x dx. And if I draw this over here, same y equals f of x, and doing this from 1, 2, 3, 4, 5, 6, 7, 8, 1 to 8, that area there represents the integral 1 to 8 of f of x dx. You can see here that the red area plus the green area equals the purple area. So in other words, the integral from 1 to 8 of f of x dx equals the integral from 1 to 4 of f of x dx plus the integral of 4 to 8 of f of x dx. In fact, this is one of the properties that we mentioned earlier. I think this was property number 4. All right, so let's just fill in what we have here. Well, we were given originally up here, okay, that the integral from 1 to 8 equal to 7. So this is 7. And we're given here the area from 8 to 4 is 3. Okay, so this one was 3. And this is what we want to find out. So this is our unknown. All right, so we're given that. So now I can just go ahead and subtract this quantity and bring it over to the other side to get what we need. So we can say that the integral from 1 to 8 of f of x dx minus the integral from 4 to 8 of f of x dx, which we said here was 7, this was 3, that's going to equal the integral from 1 to 4 of f of x dx. And since I'm subtracting them, I'm just going to get 4. 4 is my answer there. Let me just change this problem for a second. What is the integral from 4 to 1 of f of x dx? Now we could draw out figures like we did up here earlier, but let's just use some of the properties that we talked about. So again, we know the integral from 1 to 8 of f of x dx is 7. That was given to us. And we know that the integral from 4 to 8 of f of x dx equals 3. So instead of drawing out the graphs, let's just use the properties that we have here. we want this. Notice I have a 4 on the bottom and a 1 on the top. Let's use what we're given. All right, this has a 4 on the bottom, so that's good. So we have the integral from 4 to 8 of f of x dx, and we know that that's equal to 3. But now we want to end up with a 1 on the top and the 4 on the bottom. Okay, because that's what we have over here. What do I need to do to make that the same? Well, I need to have a 1 up here so that these both have 1s and they both have 4s. And to match that out, we have an 8 up here, so I need an 8 down here. Okay, well, we know that this is 3. We've got this, but that's not quite exactly the same as this one. In fact, what it is, it's flipped the 1 and the 8 here. So what I need to do is I need to flip this. So what I need is that this is going to be equal to the negative of the integral of 1 to 8 of f of x dx. And that was, I think, the second that we had there. So we have now 3 minus 7, and that's going to give us a negative 4, and that's going to give me the integral 4 to 1 of f of x dx. All right, look this stuff over, and hopefully that will help you.